remember, as you're watching this review on second semester of chemistry here at Oak Harbor High School, I would ask you to please be sure you pause the recording so that you can write down notes or catch things, back up the recording so that you can catch and see if I said what I meant to say. And if you have any questions or you think there's any errors here, be sure and talk to myself or one of the other chemistry teachers at the high school so we can get that fixed. Okay, we're going to start right in here. We're going to start right in here, clear back to stoichiometry. And remember, the word stoichiometry simply refers to using these coefficients in front of the different species in a equation to do some math to help us understand the ratio of those reactants and products. This first question is regarding a chemical called potassium superoxide, and the reaction is there with that we have had to go and balance. Be sure you balance your reaction. That's the first place to start. Assume that this person exhales 14 grams of carbon dioxide in 20 minutes. How many grams of potassium superoxide must the mass contain in order to react with the carbon dioxide that's being exhaled in this rebreathing unit? Sometimes it's good to write this 16 grams right up under the CO2 and the unknown right up under the potassium superoxide so that you can see exactly where those are going to be. But it's also important to remember that we follow this algorithm. Grams of the things we start with, convert that to moles of what we started with, convert that using the stoichiometry to the moles of what we're looking for, and then if we need to go on to the mass of the unknown, you can do that. So these numbers reflect exactly that. Here we have 14 grams of the carbon dioxide that we started with, and the molar mass is used to convert that to moles. Of course, remember, the molar mass is just the mass of one carbon and two oxygens, 44 grams per 1 mole. Now, the stoichiometric ratio that we're looking here is, if you look in the balanced equation, you'll see a 4 in front of the potassium superoxide. Where is it? There it is, right here in front of the potassium superoxide. And you will see, there we go, you'll see a 4 in front of the carbon dioxide. So be sure you practice calculating this and see if you get this answer of 22.6 grams of potassium superoxide. Great stoichiometry question. I think on your review sheet, I've now modified this so it doesn't have this word oxyacetylene here. Oxyacetylene is the process of using acetylene combined with oxygen to achieve high temperatures for cutting or welding torches. Acetylene is reacted with oxygen to produce carbon dioxide and water. A lab technician carries this process out and gets 3.16 grams of water. What is the percent yield? So as you're looking through this problem, the first thing you want to do is be sure you've balanced the chemical reaction. Did you do that? Okay, balance the chemical reaction right here. And I've written the known under the oxygen because that's what we know. And what we really want to find here is the theoretical yield of this reaction. Now you know how to find theoretical yield on a test. That's the points possible, right? Well, percent yield is what you're going to calculate eventually. Percent yield is what you actually got, like your actual score on a test or your actual yield in a chemical experiment, divided by the points possible or the theoretical yield that we're calculating up here through the stoichiometry. So we're going to calculate theoretical yield using the stoichiometry problem, starting with grams of oxygen, which cancel out here, leaving us with moles of oxygen. And then as we go to the next step, the moles of oxygen are going to cancel. We're using the stoichiometry from the balanced equation. The 2 up here in front of water, and the 5 up here in front of oxygen for the stoichiometry, and then of course the molar mass of water, 18 grams per mole. We do the math, and make sure you practice the math so that you can try this, and you should get 0.5625 grams of water. Now that is our theoretical yield for the water. What's the percent yield? Well, the percent yield is simply actual yield divided by theoretical. Calculate it and make sure you get 56.2%. Question 3. We're now moving on to a different unit. The unit we're looking at now is Unit 7, and that's where you looked at gas laws. And one of the really major things you learned when we were working with gas laws was PVNRT. PV equals nRT. This question says, though, to show how we took PV equals nRT and combined it with the formula for calculating molar mass, how we took these and derived an equation for calculating molar mass of a gas. And in lab, we did this with lighter, the gas in a lighter, which was butane, and we were able to find the molar mass of the butane using this formula. So the first step is simply to write down the two equations we're using. PV equals nRT, and moles equals mass divided by molar mass. Now the second step is simply to combine those two equations. And we're going to combine those two equations by taking this and writing it right here where the n was, just substituting that in. And that gives us mass divided by molar mass that we just wrote in here. PV equals mass times R times T divided by molar mass. And then the third step was just to rearrange that to get molar mass out here by itself, since we were solving this equation for molar mass. So those are the 3 simple steps you can do to show how to derive the equation for molar mass. Number 4, still looking at gas laws, and this time just a simple application of PV equals nRT. And so I look at this equation and I look at this problem and I say to myself, how do I decide which equation of all the equations with gas laws that I've learned, how do I decide which one to use? Well, I'm going to look at this and see if I start listing my data. I have pressure, and I have temperature, and I have moles, and of course I know R, and I'm not changing from one condition to another, so I am probably simply using PV equals nRT. Of course, I have to change my temperature into Kelvin. Atmospheres is going to work well for my pressure. I've got moles here, and the reason I have to have atmospheres for my pressures, I see right here in my value for R, I see my unit of pressure is atmospheres. If I substitute in all of these values into PV equals nRT, once I've solved it for volume, because volume is what I'm looking for, calculate the volume of the balloon, and I get 16.7 liters.